Welcome to This Explainer. Today, we're diving into something absolutely wild, the behavior of light. We're going to break down the strict, unbreakable rules light follows as it travels, bounces, and bends its way through our world. It's really less about abstract math and more of a completely visual journey. So let's get into it.
Okay, let's dive into this. You know when you look at a pencil resting in a glass of water and it just looks completely snapped in half? Or think about a coin at the bottom of a swimming pool that kind of looks like it's hovering just below the surface? Well, there's no magic here, and your eyes aren't playing tricks on you. Or actually, scratch that, they kind of are. But it's just light obeying a very specific set of rules when it jumps from one environment to another.
Here's our roadmap for today. We're starting with the magic of light. Then we'll hit World 1, Reflection and Mirrors. After that, we dive into World 2, Refraction, figure out why does light bend, and finally, wrap the whole thing up with lenses, converging, and diverging.
All right, jumping into Section 1, the magic of light. When physicists talk about everyday optical illusions, we're really just talking about light messing with our perception by suddenly shifting its speed and direction.
And that brings us to apparent depth. So, when you stand at the edge of a pool, the bottom looks a lot closer than it actually is, right? If you drop a coin in there, the light rays reflecting off that coin actually bend as they exit the water and enter the air. But here's the thing, our brains are wired to assume light always travels in perfectly straight lines. Always. So our brain traces those bent rays straight backward, creating this virtual image that makes the coin appear much shallower than it really is.
But bending is just one of the tricks. Let's shift gears to Section 2, World 1, Reflection and Mirrors. This is the world of bouncing light, where light doesn't penetrate a surface, it just bounces right off. So, the crucial point here is that this bouncing isn't just some random ricochet. It follows absolute laws. The angle that a light ray hits a surface, we call that the angle of incidence, is going to exactly equal the angle it bounces off at. Plus, the incoming ray, the bouncing ray, and that imaginary perpendicular line we call the normal, well, they all sit perfectly flat in the exact same plane. And honestly, the kicker is that this applies to every single reflective surface. It doesn't matter if it's a perfectly smooth mirror or a super rough, bumpy brick wall, the rules apply.
Now, taking a step beyond just flat mirrors, we've got spherical mirrors. You could picture these as basically pieces sliced right out of a hollow glass ball. There are two types here, concave and convex. The absolute easiest way to remember this is that a concave mirror curves inward, kind of like walking into a cave. Because of that inward shape, it catches parallel light rays and converges them together to a single focal point. A convex mirror, on the flip side, bulges outward, so it takes those light rays and diverges or scatters them away.
So, how do we actually use this in the real world? Well, if you've ever been to the dentist, you've seen them use that little angled mirror. That's a concave mirror. When an object, like your tooth, is put really close to it, it creates a virtual, upright, and highly magnified image. It's literally perfect for zooming in on teeth. Convex mirrors, though, those are the ones you see mounted high up in parking garages or on your car's side view mirrors. They shrink the image down, which gives you a way wider field of view to see what's coming around the corner.
Okay, leaving the world of bouncing light behind, we enter Section 3, World 2, Refraction. This is all about bending light. It's what happens when light doesn't bounce off but actually penetrates straight through a surface.
To really grasp refraction, we have to talk about optical density. And you've got to be careful here not to confuse this with regular mass density. You know, the stuff that dictates whether a boat floats or an anchor sinks. Like oil floats on top of water, right? That's because it has a lower physical density. But optically speaking, oil is actually denser than water. Optical density is purely about how much resistance light feels as it moves through something. The higher that optical density is, the more the light is literally forced to hit the brakes and slow down.
Now, what's really interesting about this slide is this massive number right here, 300 million meters per second. That is the absolute maximum speed limit of our universe. That's how fast light travels in a perfect vacuum, where there is exactly zero optical density to get in its way. It is just blindingly fast. But the second that light slams into water or glass or oil, it slows down. And scientists measure that slowdown using something called the refractive index. You can look at this in two ways. First, there's the absolute refractive index, which compares a material straight against that perfect vacuum speed. So if a piece of glass has an index of 2, it basically means light travels exactly half as fast in there compared to a vacuum.
Then there's the relative refractive index. Think of this like comparing test scores with your buddy instead of against a perfect 100. It's just comparing the speed of light between two random everyday mediums, like how fast it moves in water compared directly to how fast it moves in glass.
So we know light slows down, but that brings us to section 4. Why does light bend? Let's look at the mechanics. The big question here is, why on earth does changing speed force a ray of light to actually change its physical direction?
To visualize this, I want you to imagine you're driving a really fast car down a beautifully smooth, freshly paved road, and suddenly you veer off and hit a thick patch of mud. But you don't hit it straight on, you hit it at an angle.
Let's walk through exactly what happens to your car, because it perfectly mirrors what happens to a light wave. Step 1. Since you hit the mud at an angle, one front tire hits the mud first and it immediately bogs down. Step 2. Your other front tire is still out there on the smooth pavement, spinning incredibly fast. Step 3. That massive difference in speed between your two front tires basically forces the entire axle to pivot. The car violently jerks and bends its path right into the mud. And guess what? That is exactly what happens to light. When a light wave hits a denser medium, like glass, at an angle, one side of the wave slows down before the other side does, forcing the whole ray to pivot and bend.
The cool thing is, this pivoting action isn't random, it's entirely predictable, and it's governed by Snell's law. It basically says that if you take the sine of the angle the light comes in at and divide it by the sine of the angle it bends into, you'll always get a constant number. And brilliantly, that constant number is the exact same refractive index we just talked about, so the math perfectly proves exactly how much our car is going to bend.
Let's move to section 5, lenses, converging and diverging, and see how this all builds together. This is where we take that bending power of refraction and purposefully shape it to manipulate images.
Lenses basically act like the alter egos of mirrors. A convex lens bulges outward, sure, but unlike a convex mirror, it uses refraction to bend and converge light rays into a single focal point. Think of a convex lens almost like a tailor stitching up a rip in a piece of fabric. It pinches the light rays closed. A concave lens, which is thinner in the middle, does the exact opposite. It bends the light to spread it out, diverging those rays far away from each other.
If you ever find yourself needing to figure out how an image will look through a lens, you really only need to remember 2 shortcut rules. First, any light ray coming in perfectly parallel to the lens is always going to be bent to pass directly through the focal point. Second, any light ray that passes dead center through the very middle of the lens, the optical center, will just completely ignore all the rules of bending and travel perfectly straight without any deviation at all.
The ability of a lens to actually pull off these tricks is called its power. It's denoted by a really simple formula. P equals 1 divided by the focal length in meters. Basically, the shorter the focal length, meaning the quicker the lens forces the light to pinch together or spread apart, the higher the power of that lens. It's just bending the light way more aggressively.
And this whole thing just brilliantly illustrates the delicate, intricate dance between light and matter. Which leaves us with a final thought to chew on. If light's path is constantly being sped up, slowed down, and bent by the optical density of literally every transparent thing it touches, can we ever truly trust where an object appears to be in the vast, shifting density of our universe? Next time you look through a simple glass of water, just remember, you aren't really seeing reality. You're just seeing the rules of refraction at play. Thanks for joining me for this explainer, and keep questioning what you see.